Good afternoon. Thank you for attending the Senior Design Showcase. We are the graduating class from CE 488. The speakers will be Jared, Emily, Eduardo, Andrew, and myself, Cheyenne. We will be presenting the project, What to Do with All This Water.
Thank you. So the senior design class worked in groups to design a potable water system for the designated location. Over the past 3 decades, CSUN has increased dramatically. And for this reason, new methods for properly utilizing the current water distribution system must be implemented. Currently, there is a flooding problem on the West University Drive during the rainy season. In order to better utilize the runoff as well as create a safe environment for students, a drainage system and water network will be explored. Through our work, the designated system will tackle the flooding problem that will ultimately create a safe environment for students. Moving on, let's take a look at our project's location. This section is bounded by these coordinates and includes the extended University Commons, University Hall, and parking lots B4 and B5. In order to design a potable water system, the group will take a virtual visit and the site using Google Earth Pro. It is important to evaluate new ways in which water can be collected and treated for future use. And our analysis will go into turning the potential hazard of water flooding into the location and help the university put a less demand on the city's water supply.
Hello, everyone. I'll be talking a little bit about the theory behind the project. It involves fluid mechanics and hydrology, specifically the Bernoulli's equation, which is based on the work energy principle or conservation of energy. We assume the pipe is full, flow is steady, incompressible, and inviscid. After this assumption, we assume continuity. So Q1 equals Q2. That comes from the conservation of mass, which we can also say that the area 1 times the velocity 1 equals the area 2 times the velocity 2. Mixing Bernoulli's equation with Darcy's equation, which was also done for us on EPA net, we find the total head loss. With this, we can find the diameter of pipes for our system. Each group used different steel pipes for their project. Some use cast iron, others use stainless steel. But regardless, it seemed that steel was the favorite for its excellent resistance to high internal pressures and pressure surges. Large diameter steel pipes are normally used for these types of systems and wastewater applications. Some of the methods used to make these type of pipes are seamless, which you can see on the bottom right, welded, which you can see on the bottom left, and cast molded, which is on the top. Steel is a great material, although it corrodes, it typically doesn't crack, and instead of breaking, it bends.
So this slide here just shows how one of the teams was able to get some data into the model. The table on the right is a roughness coefficient table that is actually from EPA Net's user manual. So it's like defined by the software. And then some dimensions that we chose for our water system. We had 10-inch diameter water mains. Lateral water supply lines were 2 inches. Fire hydrant supply lines were 10 inches. And then we also provided 4.5-inch supply lines for the parking structure fire sprinkler system.
Getting into some of the more specific site conditions, the first problem we asked ourselves was exactly how much water can we capture? So using Google Earth Pro, we captured a satellite image of the estimated area that we can capture, and then scaling it with AutoCAD and then drawing a polyline and taking the area inside. We were able to estimate it's around 30 acre. We also use this method to define a flow path. And then we also were able to capture elevations to determine the slope of the entire area. We found it was mostly flat, and living in this and looking into the weather data, we found it was a very arid climate. According to average weather in the area, it rains about 3.4 inches per year, and most of it is during the months October and April, with a very, very low chance of rain in the middling months during the dry season. Next, we asked ourselves, how do we estimate the demand of these buildings that the people inside will have? Since they're office buildings, we typically don't inspect super full rooms. So we assumed one person per window and 15 gallons per person per day. Calculating a yearly demand that both buildings will put on the stormwater that we capture, and the rest will be repurposed for irrigation of neighboring bushes, trees, and plants along these buildings.
So here we're showing how one of the groups is able to get elevation data into AutoCAD Civil 3D. Basically, we got like a topographic map available online, and we were able to trace the contour lines using the polyline tool and then assign individual elevations to those polylines. From there, we're able to build a surface in Civil 3D, and basically the surface interpolates between the polylines and gives us like a nice three-dimensional surface that we can label spot elevations on. And so we're able to get like elevation data to a pretty good degree of accuracy with this method. So this is an example of how one of the groups was able to utilize LA County Department of Public Works standard details in order to compile minor loss information for lateral lines. So we have like a table here on the right side that we use to like count however many elbows and other minor loss components like that were in the system. So basically we had like backflow preventers and water meters that were contributing extra minor losses for the lateral connections. And once we sum them up, we were able to input them into EPA net in a manner similar to what's outlined there. This is another use of the Department of Public Works standards here, showing what our minimum depth of cover would need to be for a main line of a 10-inch diameter. So here's like an overview of the model that we created in Civil 3D. It was really useful using software like this because it really helped to, it was a lot of work, but it really helped us to imagine the model. And then once we had everything labeled properly, we're able to go back and forth between Civil 3D and EPA net and like make the corresponding changes that we needed to make. Here's just another slide showing the total network outline, and then there it is graphically represented in EPA net. On the right side, those are just some tables showing like where we're able to input properties for the different pipes and the junctions that are in the system.
So as we mentioned earlier, one of the main goals of this project was to supply a section of CSUN with potable water. So in order to do that, we needed to explore options for treating it. The good news for us is that rather than treating wastewater, we are mainly going to be treating typical surface water from the rain. So just a little background, a standard process for potable water treatment involves water from a lake, reservoir, or river being transferred into a tank where coagulation and flocculation occurs. So there, floc is formed and is going to settle at the bottom of the water. And then the clear water on top is filtered and a disinfectant may be added at the end. So water can be treated at centralized or decentralized treatment systems, but for a project of this magnitude, we felt a decentralized system was the best option. So instead of sending the water to a different facility to be treated, we would treat it on site. So one option that we considered was a containerized treatment system. These systems offer lower costs than comparable field-erected buildings. They're relatively easier to install. And if we were to expand the scope of the project, we would just add more containers. So at CSUN, this would be a suitable option. So if you look at the area of our project, including the university buildings, the parking structure, and all the parking spaces, what you'll find is that there's not too much space available. Because containerized systems are compact, we won't have to worry too much about space, and we'll have some flexibility on where we can install these. Ideal spots for these containers lie between University Hall and extended University Commons, or just outside the parking structure.
Next, we had to look into the actual drainage and how much water we're going to get per storm in order to capture. So the first, to capture per storm, we input some of the site conditions into HydroCalc using some of the LA County values. And for an 85 percentile common storm, using an impervious data, we gathered a clear runoff value, and then we subtracted a pre-developed value where we use a much less percent impervious value. And then we found the volume to mitigate that we need to capture per storm of around 23,500 cubic feet. That's around 170,000 gallons. And then to actually prevent flooding, we needed to design for a 50-year storm peak flow. And then we input the values, the similar site conditions into HydroCalc. And then we found we need a peak flow of around 43 CFS that we need to be able to drain and handle.
So this slide here is just kind of summarizing some data outputs that we were able to get from EPAnet. It's actually pretty nice. It has like a graphical interface and it color codes. I displayed pressure and velocity because those are some things that are of particular interest in water networks. So our design goal was not to exceed 80 PSI, just kind of something we defined for ourselves because, we didn't want to put excess wear on the system. And we were able to achieve that. I think max pressure was 78 PSI, whereas the system inlet was 80 PSI. And then the highest velocity we recorded in the model was 7.45 feet per second, which I think was a little high, but we don't really want to get the velocity to be near 10 feet per second due to frictional losses that'll occur.
Right, so leading into the water system recommendations and evaluations, we decided that this was the most efficient water treatment system available. As the area is relatively small compared to most projects in magnitude, storm check chambers were recommended for the installation. The volume of the calculated water storage was needed is based on an 85% tile storm. Moving on, we'd like to discuss that the parking area of the underground storm check water chambers could capture about 2,555 CS. This would be a relatively good location between parking lot B4 and B5. Also, we'd like to consider that the proposed system will decrease the flooding on the West University Drive and create a safer environment for not only students, faculty, and every other guest in CSUN. It is important to select the most and maybe cheap containerized system. Okay, I'll continue though. With concluding our presentation, I do want to mention that we did have an amazing time studying our piping systems, as well as learning how to do the estimation techniques for this water demand, as it was one of the most important projects of our senior design course. It was very vital to practice some of these different software programs as we will be moving on to our professional development projects in the future. And our references are as listed. Thank you.
Thank you. Any questions from the judges for what to do with all this water?
Yeah, well, very impressive. I'm hoping the institution is going to do something like this. So that's one question. Is CSUN going to implement? And then secondly, is this practical for residential consideration?
I can answer that. I think the flow demands would definitely change if it was a residential system, because we designed it based on the fact that these are office or school type buildings. So the flow demand estimation would definitely change. And I think a lot of us were kind of struggling with like figuring out what the size of the pipings needed to be and stuff. There's not a lot of information available on water mains. So definitely maybe could go down a little bit. I think we kind of went overkill with the 10-inch pipe, but yeah, I guess, I don't know if CSUN's planning on implementing anything like this.
Hope so.
Okay, I have a question out here. What do you do with the water after you've collected it?
I can also answer that. So originally we thought this project was going to be like a runoff, sort of like a stormwater system. But once we got the assignment, it was actually a potable water network. So it's kind of a curveball thrown to us at the last minute. But yeah, so the the runoff that we stored in the storm tech chambers, those can actually be buried underground, and they're multi-use. So we can actually scale them up. They're modular chambers, and we can line the bottom. So if we want to hold on to some of that water to pump back up to the land, irrigate the landscape, we can do that. And if we want to just leave the bottom of the chamber unlined and let the water infiltrate, we can also do that and recharge the aquifers, you know, down below. So yeah, we definitely could have done a little bit more in depth on the like runoff, what we're going to end up doing with it. But some of the groups even went in to treat the water and repump it back into the buildings for use in the potable network system.
Thank you.
Good job, guys. Great presentation.
Thank you.
Any other questions from anybody in the audience? I see one in the Q&A. Great concept. Not sure if you covered, had to leave. Okay. What is the return period? What's the cost analysis? What was the cost analysis done? What's the return on investment period for this project?
We're starting to look into like actual implementation of all the pipes and like how it does, but there was so much new things that we were kind of making mistakes and then correcting ourselves that we did run out of time, and we were not able to do a cost analysis section of it, even though it is very important. But we don't know return on it yet, but
okay,
that's just how it is.
Okay, any other questions from anybody? There is one second. This is from Ricardo Medina. Did you consider time of use? What happens to your treatment system during off-peak hours?
So my team actually, we didn't consider like off hours, but what we did is we modeled fire flow. So we had systems going to fire hydrants, and we increased the demand at those hydrants like locally for like, you know, just simulating a fire, just to check the system again and see if all the pressures were still in a good standing. And everything looked good to me. The velocities definitely increased, but not to the point where it was like, you know, excessive, in my opinion.
Okay. Any other questions? We have. Okay, I think that's it. Thank you so much. Appreciate it.